Okay, yesterday we were discussing a few physical consequences of the Lorentz transformations. Okay, so we had the Lorentz transformations, gamma, delta x. Okay. Delta t prime is equal to gamma delta t minus v by c square delta x. Okay, and the first consequence we discussed was simultaneity. We said that simultaneity is relative. Okay, simultaneity is relative. Right? Yeah. So we saw from here that if two events are simultaneous in one frame, okay, if delta t is 0, then you see that delta t prime is not equal to 0. It's gamma minus gamma v by c square delta x. Right? But you notice that if delta x, I had to tell this also, if delta x is 0, if the separation, okay, what's the x direction here? The x direction we have taken as the direction of the relative velocity. Right? What's the direction at which the s prime moves with respect to s? We assumed all along that we can always align our x-axis with this direction of velocity. And we have written down equations corresponding to that. Right? So if the events are separated, okay, if the events are separated, if delta x is not equal to 0, then simultaneity is not relative. But if they are happening at the same point, right? If they are happening at the same point, then observers would agree that they are actually simultaneous. Okay, is that clear? Similarly, this can be separated like this also. Two events can be separated like this in such a way that delta x is equal to 0 and delta y is not equal to 0. Right? So if you draw a line, joining the two events that you're talking about, right? If you take a line joining the events that you are talking about, right? And if this line has no component, right, or if the velocity has no component along this direction, if the velocity has no component in this direction, then simultaneity is preserved. All right, people agree that events are simultaneous. So people would agree that these two events are simultaneous. Okay, these two events are simultaneous. All right, and people, yeah, this means that this, if you take, yeah, these two events are simultaneous. These two are not simultaneous. These two are also not simultaneous. Right, so you've got this delta x. Delta x equal to 0, then they are simultaneous. If they are happening at the same point, okay, then you don't have problem with simultaneity. Okay, right. We also discussed time dilation and length contraction. We had this result. We can just say delta t is equal to delta t0 divided by square root of 1 minus v square by c square. We also got it from the Lorentz transformation equations. We also had this, okay, measured length L is equal to L0 1 minus v square by c square. Okay. All right. So much is clear. Now we can just start doing problems. We said that this is proper time. Proper time. That's the time shown in a clock which is at rest in the frame that you are talking about. Okay. We said it's a Lorentz invariant quantity. We haven't proven it yet. We'll be doing it soon. Okay. All right. Now let's go to the problems. Let's go to the problems. Okay, let's do an example first. Okay. Relativity of geometric angle. Relativity of geometric angle. Okay. So you can consider a rod. Okay, this is a rod with proper length L0. Okay, it's moving with speed v. It's moving with speed v. All right. Let theta 0. Theta 0 is the angle. Theta 0 is the angle between the velocity vector and the length of rod. Right. Velocity vector. This is the velocity. It's moving like that. Okay. This is the velocity vector. All right. Yeah. Theta be the velocity. Theta 0 be the angle between the velocity vector and length of rod in the rest frame of the rod. Right? So this is the rest frame of the rod. Right? So you can imagine an observer moving at a velocity v in the opposite direction, or we can imagine that it is moving left. Right? Okay, so we see from here that, okay, so we know that the length contraction happens only along the direction of motion, right? The length contraction happens only along the direction of motion, not in perpendicular direction. Okay, all right. So we have to take the component of length, okay, or you have to take the part of the length which is parallel to the velocity, and only in that direction there will be a contraction. Okay, so we can write from here. We can write from here tan theta 0. In other words, we can ask whether the velocity has a component along the length, right? We can ask this question: does the velocity have a component along the direction of length? And only that component of velocity will cause length contraction. Okay, not the whole velocity. Only the component of velocity along the direction of the length. Okay, along the direction in which the rod lies. Okay? So tan theta 0 is equal to, this is Ly and Lx. So this is equal to Ly by Lx, right? Okay. Yeah, that's the definition of tan theta. Tan theta is equal to Ly divided by Lx. All right. Now, suppose this is in a moving frame. All right. Now you are looking at it from the moving frame. This is in the rest frame. All right. This is just a direction. Now you are looking at it from a frame which is moving at a velocity v along this x direction. All right. So that length we can write it as. So this is moving. And we know that the length will change. Generally, we'll call this as Ly prime and Lx prime, and this new angle as theta. All right. So the new angle would be tan theta is equal to Ly prime by Lx prime. Okay. Is this clear? It's no problem, right? But you see that Ly prime is equal to Ly, no problem. But Lx prime, all right? Lx prime, you're looking at this length, all right? This Lx. You're looking at this length from a moving frame. So that would shorten Lx multiplied by 1 minus v square by c square. Is this clear? But we already have this Ly by Lx equal to tan theta 0. So you see that this is equal to tan theta 0 divided by square root of 1 minus v square by c square. Okay, so you see that tan theta is equal to tan theta 0 divided by square root of 1 minus v square by c square. Okay, or you say tan theta 0 is equal to tan theta multiplied by square root of 1 minus v square by c square, which means that tan theta is greater than tan theta 0. Right? Tan theta is greater than tan theta 0. Right? So the angle increases. The angle increases, or we can say that theta is greater than theta 0. Okay. So geometrical angle, okay, made by an object. Geometrical angle made by an object. Yeah, the geometrical angle made by an object increases. Right, if you're measuring it from a frame which is moving, which has some component along this length. Right, that's the idea. So geometrical angle increases basically if the velocity in which you are moving has a component along the direction of length. Okay, so yeah, such questions can be asked. You know the method now, you can easily solve such problems. Okay, is that clear? Is there any doubt?
No, sir, it's clear.
Now there can be problem. I will just say this: relativity of angle made by velocity vector. Right. Another example. We won't do this completely. We'll just give the idea and we'll solve problems. Relativity of angle made by velocity vector. Okay. So let velocity of a particle make an angle theta with the plus x direction in S frame. Okay. So you are looking at, this is the S frame and this is the velocity vector. It makes an angle theta with plus x direction in S frame, and its velocity makes an angle theta prime in S prime frame. All right. In S prime, this is S prime. This is the velocity vector. Let's call it as Vp prime. We'll call this as Vp. Okay, so imagine that this is some particle P moving, okay? And let this be theta prime. Now, how are these these relative angles related? Okay, so from here you see that, okay, this component is Vx. Here this component is Vx prime. Right. So from here you see that cos theta is equal to, or we can say Vx. Okay, Vx equal to Vp. It's correct, right? Yeah. Cos theta, right? Yeah, Vx equal to Vp cos theta. All right, and Vy is equal to Vp sin theta, right? Okay. Now, what about cos theta prime? Oh, yeah, this is fine. Okay, from here we can write cos theta prime is equal to, or Vx prime is equal to, you can write it anyway. Right, you can write Vx prime is equal to Vp prime, right? This is the component here. Vp prime cos theta prime. Right. Vx prime is equal to Vp prime cos theta prime. Okay. All right. Now what we can do, okay, what we can do is, right, okay, now what we can do is this, we can find, we know the transformation equations for velocities, we can find Vx prime in terms of Vx, right? We can find Vx prime in terms of Vx, and correspondingly we can find Vp prime in terms of Vp, and then we can relate these two angles, all right? So we'll also use the velocity addition formula. We'll see a problem of this model, all right? You also use the velocity addition. Okay, and you just do the transformations, and you can relate the angles, right? You can relate the angles also by using the velocity addition formula. Okay, so such problems also will be asked. We'll see a problem of that form. Okay, so when you see the problem, you will know what to do. You may also need this thing. Vp here is Vx square plus Vy square in 2 dimensions. Here Vp prime is equal to square root of Vx prime square plus Vy prime square. Okay, all right. So you keep this as such. You can change this Vx prime and Vy prime in terms of Vx and Vy and the other quantities. All right, and then you can relate these two things to find the angle. All right. Okay. Or whatever relation has been asked, this can be done. So when you do the velocity addition formula, you have to be careful. Again, we'll see, you'll have to take the component of the velocity. Let's do a problem. Okay, so here's a problem. A car is moving with speed c by 2. A car is moving with speed c by 2. A light beam is emitted from the car at angle 45 degree with the direction of velocity of car. So we've got a car moving. This is a problem. Okay, we have got a car moving. We have got a car moving. So with respect to ground, we have got a car moving with velocity c by 2, right? And a light beam is emitted from car at angle 45 degree, right? This is speed c, and it makes an angle 45 degree with the car, right? 45 degree with the velocity vector of the car. Okay. What is the angle with velocity vector as seen from ground? What is the angle with velocity vector as seen from ground? Okay, that's the question. Now, how do you do this? Okay, how do we do this? This is just an example of what we are talking about. What's the angle with velocity vector as seen from the ground? Okay. So it's 45 degree as seen from the car. What's the angle as seen from the ground? Okay, now we know that this speed, okay, we can call this as Vp prime because it's seen from the car. Vp prime is equal to c. Okay, we immediately know that Vp is also equal to C because this does not change. Okay, the speed of light is invariant for all frames. So we'll just write down whatever we have. Right now, we can write V prime is equal to C by 2. That's the speed of the car. We can call it as V, simply V. Okay, I think it's better to write this as UP prime. Okay, that's we'll just write it as U. Imagine it's a photon or something. Okay, UP prime is equal to C, UP is equal to C. So V is equal to C by 2. That's the speed of the car. Okay, so you see that let's call U. Right, so that we don't have any indices. Right, so you see that. See that ux prime, right, the x component of this speed of light, that's equal to Vp prime. I'm sorry. Ux prime is equal to U cos 45 degree. And what is U? U is equal to C. So it's equal to C divided by root 2. Okay, that's Ux prime. So it's C divided by root 2. Okay, now we have to use the velocity. We need to find U, Ux. Okay, we've got Ux prime, we have got V, we need to find Ux. Okay, what's Ux? What's Ux? Is it more or less? Is it more or less? Right? We know that we can we have these velocities. We have got Ux prime and we have got V, which is the speed of the car, divided by 1 Ux prime V by C square. It's a plus or minus over there. This is the x component of the velocity C as seen from the car, okay, moving parallel to it. Right? So what happens when you're looking at it from the ground? Will it be more or less? Should I put a plus there or minus there? A quick answer. Should I give a plus or minus there? Just think about it physically, all right? So this is the x component as measured from the car moving along the x direction. Right? Now you are watching it from the ground. What do you expect? Should it be a plus or a minus? Is anyone going to answer? Yes?
It increases, sir.
Increases good. So you'll have a plus there, right? Okay, you can remember it from the transformation equations, but you don't have to. Okay, so this is the velocity as measured by moving parallel to it in a car. Okay, so when you look from ground, of course, you will have it increased. Okay, you'll have a greater velocity. Right? Okay, so this becomes Ux equal to Ux prime plus V, 1 plus Ux prime. So you just substitute these things. We have got Ux prime as C by root 2. Okay, what's V? V is equal to C by 2 divided by 1 plus Ux prime V by C square. So 1 by C square. What's Ux prime V? Just C by root 2 multiplied by C by 2. So it's C square by 2 root 2. So the C square and C square get cancelled. So you simply have 1 by 2 root 2. 1 divided by 2 root 2. Okay. All right. So this we can simply write as, maybe you don't have to simplify it too much. We can simply write this as, okay, you see that we've got a 2 root 2 there. You just take LCM. Okay, you just add these things and you can simplify this too. This is 2 root 2. So it's 2c plus root 2c, right? So it's c multiplied by 2 plus root 2. Okay, so this is, let's write it. So this is equal to divided by 2 root 2 plus 1 divided by 2 root 2. Okay, so that's equal to, okay, that is equal to 2 plus root 2 divided by 2 root 2 C divided by 1 plus okay, right. So what do you get? You see that ux is equal to, you check the numerical thing, okay? Right, that's equal to 2 root 2 plus root 2 divided by 1 plus 2 root 2 multiplied by C. Okay, is that fine? Can we simplify it further? I think that's fine. Okay, can you check whether this calculation is correct? Just check whether this is correct. All right, this part is correct. Just see if the addition is correct. Okay, so it's C multiplied by 1 by root 2 plus 1 by 2 divided by 1 plus 1 by 2 root 2. I think that's correct, right? Okay, we have got ux. Okay, we have got ux. So what we are saying is in the frame S, ux we have got, and we also have this u. Okay, what was u? U was equal to c. So what's the angle theta? We can call this angle theta or theta 0, right? What is theta 0? You see that theta 0 cos theta 0 is equal to, from here is that cos theta 0 is equal to ux by c, right? Ux by c, or theta 0 is equal to cos inverse ux by c, right? So this c gets cancelled. That's equal to cos inverse of 2 plus root 2 divided by 1 plus 2 root 2. Okay, so that's the answer. So this is the angle as observed from the ground. Okay, we can check using a calculator what this angle exactly is. Okay, I don't think it's any standard angle, but this is how you get the answer. All right, so it's not quite 45 degrees. You see that it's different from 45 degrees as observed from the ground. Okay, I hope this is clear. This is fine. This is okay.
Yes.
Is there any question? Is there any doubt? So the first thing so we were asked to find the angle in a different frame. So what we first did was we found, okay, we wrote down what we know. We have got u prime equal to c, so u is also c, okay, and the v is also given as c. We have ux prime. We find ux prime there, all right, and you find ux using the velocity addition rule, all right, and we have all the information necessary to find ux. You find ux, and then cos theta is equal to ux by this velocity, right? So that's rather simple. Okay. Let's do another one. Okay, here is a problem using length contraction. A rod of length L0, so L0 it means proper length. The rod of length L0 moves with speed c by 2. Okay, moves with speed c by 2 with respect to an observer such that the velocity of a rod makes 45 degrees with its length. Okay, such that the velocity of the rod makes 45 degrees with its length. Okay, find the length of the rod measured by the observer. Okay, so you've got this observer. You've got this observer, and your length L0. This is moving at an angle. What do you say? 45 degrees. Yeah. Okay, 45 degrees. Find the length of rod measured by the observer. Okay. All right. So this is speed c by 2. That's the speed c by 2. Okay. All right. So we know that only the velocity, the component of velocity along the direction. Okay. So only the component of velocity along the direction of motion will contribute to the length contraction. Okay. Okay, so this is the observer. So at what velocity is the rod moving, right? With respect to this observer, you see that the component of velocity we can write simply as v. We don't have so many velocities, so we'll simply write this as v. Okay, v is equal to c by 2 cos 45. Okay, we can write it vx if you want. That's equal to c by 2 multiplied by 1 by root 2. Okay, so that's equal to c by 2 root 2. Right? Okay. So the observer says that the rod has a velocity parallel to its length, and the component of velocity along the direction is c by 2 cos 45 degree. Right. So now you just use the length contraction idea. This is the velocity you will have to use. Okay. You see that L equal to L0 square root of 1 minus v square by c square. So L0 is already given. It's given as L0, so it's equal to L0 multiplied by square root of 1 minus v square by c square would be, this is c square by 4, 2. So 1 by 8. Okay. So that's equal to root 7 L0 by 2 root 2. Okay. Yeah. So that's the length as observed by this observer. Okay. Just a moment. All right, so this is not, I'm sorry about this. So the question is like this, okay? A rod of rest length L0 moves with speed c by 2 with respect to an observer. It's going like this. This is the rod of length L0, okay? I'm sorry. This is the rod of length L0. This way it's not correct, okay? This is the rod of length L0 and it's moving with the velocity c by 2. Okay, this is what's happening, right? So the observer sees that it's moving like that and he will see that only the, this is 45 degree, okay? So the observer will see that only the x component of this velocity will contribute, only the component of velocity along the direction, along the length, only the component of velocity along the length will contribute to length contraction. All right, that's why we are finding c by 2 cos 45 there. Is this clear now? Actually, I'm sorry about this. So this is length L0, okay? This is length L0, right? And it's moving at an angle 45 degree with the velocity c by 2. Okay, this is how I should have drawn the diagram. Okay, I apologize for the mistake. I hope it's clear now. Is there any confusion there? Is there any confusion? Shall we go to the next one? Yeah, should I explain it again? All right, good. Okay, so this is the question. We have got a rod of length L0. Okay, this is the question. We have got a rod of length L0 and some observer says that it's moving at velocity c by 2 at an angle 45 degree, right? At an angle 45 degree, okay, with respect to the length of the rod. Okay, this is right, and we know that only the component of velocity along the length of the rod, right? So the length contraction formula applies only for if you are moving parallel to it. Okay, this component, right, this perpendicular, if you are moving like this length does not change. If you're moving like this, only this length will change. Okay, All right. So this velocity has two components. This velocity vector has two components, one along this direction and one along this direction. All right. And only the velocity component along this direction will contribute to length contraction. All right. Only the component of velocity along this direction will cause length contraction. Is that clear? Because the length contraction happens only in the direction parallel to the direction of motion. Is it clear now?
Yes, sir.
Yeah. So the whole c by 2 does not cause length contraction, but only the component along the length. Okay. So only the component along the length or parallel to the length, okay, causes length contraction. The perpendicular velocity does not cause any length contraction. All right. So that's the reason why we don't take c by 2 as the whole velocity, but only the x component of it as the velocity. All right. So instead of v here, we should take this quantity. All right, the x component of this, only the component parallel to the direction of the length. This is clear now. Yeah.
Yes, sir.
Yes, sir.
Okay, good. Sorry, I was a bit distracted in the beginning. Okay. So I hope I didn't cause any confusion there. All right. Here is a nice question. A rod is moving its speed c by 2. Okay, here we have to combine some of the concepts that we have used before. A rod is moving its speed c by 2, with respect to ground, such that velocity of rod is parallel to its length. Okay, such that velocity of the rod is parallel to its length. Okay, this is fine. Okay, so we have got in the ground frame, we have got a, let's say, meter scale moving at a speed c by 2, right, parallel to the ground. Okay, and the velocity is in the same direction. Right, velocity is the same direction as the in which the length lies. Right, in which your meter stick lies. Okay. Now the question is this. So the rod is moving its c by 2 with respect to ground such that the velocity of rod is parallel to its length. No problem. All the velocity is parallel to the length. No problem there. An observer is also running in the same direction with speed c by 3. Okay. An observer is also running in the same direction with speed c by 3 with respect to ground. Okay. If rest length of the rod is L0, find the length of the rod as measured by the observer. What's the length of the rod? Okay, what is L? As measured by this observer who is moving it c by 3. All right. So we have got, so what we do here, we have got the speed of the rod, we have got the velocity of the rod with respect to ground. All right. We have got ground, we have got this rod moving with c by 2 with respect to ground. All right. And there is another observer who is moving at a speed c by 3 in the same direction. All right. So what's the length measured by this observer? The question is, what's the length measured by this observer? All right. So in order to find the length measured by this observer, we first need to find the velocity of the rod with respect to this observer. Am I right? We need to find the velocity of the rod with respect to this observer. Am I correct? Yeah. So we know the velocity of all these things with respect to the ground. Okay, that's the ground. Right. So we know the velocity of this thing with respect to ground. That's c by 2. We know the velocity of this person who is running in the same direction with speed c by 3. Right. That's also known. Okay. So what's the velocity? What's the velocity of the rod with respect to running observer? Okay. So give me that velocity. Let me write it as v. Okay, I'll write this as velocity. What's this velocity? We know that you have to use the addition of velocities formula. So if it's Galilean, c by 2 and c by 3, is it a plus or minus here? Plus or minus? Plus or minus?
Minus.
Okay, so you'll see that it is minus there. All right, that's good. Okay, and 1 by 6 because it is it is c by 2 multiplied by c by 3 divided by c square. So it is 1 by 6. Am I right? Is it 1 by 6? Yes. Okay. So this is equal to, you see that this is equal to, so here also you have a 6. So 3c minus 2c. So it's c by 6 divided by 5 by 6. Okay. So that's equal to c divided by 5. C divided by 5. Right. Now you know the velocity at which this rod is moving with respect to this observer. So what's the length measured by this observer? It would be L is equal to L0 square root of 1 minus V square by C square. Right. So it would be C square by 25 divided by C square. So it's 1 by 25. Am I correct? So that's equal to. So if you do that, what do you get? L0 square root of 25 minus 1 is 24 by 25. Okay. All right. What square root of 24? 24 we can write as 6 multiplied by 4. So 6 will remain inside the square root. So it is 2 root 6. Right? Yeah. 2 root 6 divided by 5 L0. Okay. That would be the final answer. Okay. All right. We'll hope that's clear. Next question. This was asked for a previous net exam. Okay, I don't remember which year, but this was asked. So question is this: a circle of radius r, is moved parallel to its surface. Okay, it's moved parallel to its surface with speed 3c divided by 5. With speed 3c divided by 5. Okay, you've got a circle that's moving with 3c divided by 5. Okay, because of which it takes shape of an ellipse. Find the semi-major and semi-minor axis of the ellipse and the area. Right. So you need to find semi-major, semi-minor axis and area. Okay. So you have got this moving at 3c divided by 5. So let's look at it. We have got a circle which is moving at 3c by 5 with respect to ground. So with respect to ground, you will see that the length contracts along this direction. So you will see something like that. Okay. So that's what happens. Okay, you see that the length contracts along this direction. This remains the same. Okay, this length remains the same. So what you see is something like this. Okay, this length is r itself, or this is 2r. Okay, this length is the diameter, that's equal to 2r. It remains the same as this. Okay, what about this length? That decreases. Okay, how much does it decrease? You know how the length contraction works. So you can find the new area as the new radius. So let's call this as, what's this called? This is A and this B. All right. Yeah. So B is equal to, okay, B is equal to R. It's less square root of 1 minus B square by C square. Okay. A is equal to R itself. Okay. A is equal to R itself. So A remains as R. Okay. B becomes R multiplied by square root of 1 minus V square by C square. Is this clear? So that's equal to R square root of 1 minus V square is 9c square by 25 divided by c square. So it's simply 9 by 25. Okay, and that's equal to, so if you do this, 25 minus 9 is 16, square root of 16 is 4, so it's 4 by 5. Okay, 4r divided by 5. Okay, so B is equal to 4r divided by 5. Okay, and A remains the same. Yes.
അതിന്റെ 1/2 പോലെ സാറേ.
അല്ല, r ന്ന് എടുത്തിരിക്കുന്നത് 2r എന്നല്ല.
Okay.
Okay. So what's the area now? What's the new area? Okay, problem of this, you know, the ellipse, area of the ellipse is pi AB. Okay, area of ellipse is pi AB. Okay, pi AB. All right. So this becomes pi. We'll just write the whole thing again. We'll see some pattern there. So we can just substitute this for the exam and find it, but let's write it as pi A is R and B is R multiplied by square root of 1 minus V square by C square. So it's equal to pi R square root of 1 minus V square by C square. Right? You could simply multiply this. Okay, I just want to show that the area also goes like this. This is equal to A is equal to A0 square root of 1 minus V square by C square. Right? I just wanted to show this to you. Okay, A is equal to A0 multiplied by square root of 1 minus V square by C square. So you can just use this formula or you can multiply pi AB here, right? And the final answer would be, so you just multiply these things. We already found this. So the area is equal to, new area is equal to pi R. So 4 by 5 pi R square, right? 4 by 5 pi R square. Okay, all right. Now, if the details of the shape is not given, you can always try this. Because it's ellipse, we could use this pi AB formula. If the details of this ellipse is not given, or details of the shape of your object or the shape of the area is not given, you can always use this formula. Okay. So it goes just as length. It goes just as length. And you can prove that easily. If you look at an area, it's integral dx dy, right? So in a plane, okay, and you'll see that only one of them will change by a factor of square root of 1 minus v square by c square. That can be pulled out of the integral, and what you get is square root of 1 minus v square by c square multiplied by the old area. All right, so that's not very difficult. You remember this relation. Okay, in the same way, you see that volumes also go like this. Okay, volumes also change in that manner. Okay. All right. Now let's do a time dilation problem. I think we have covered all sorts of problems using length contraction. Okay, so a problem of this form might be asked, or some combination of this form. Okay. Now let's look at time dilation. Time dilation we are already familiar with. Okay, we know that delta t is equal to delta t0 divided by square root of 1 minus v square by c square. Okay, and this particular effect has attracted the imagination of all sorts of people, right? Scientists or laymen, right? Because there are things like the twin paradox, etc. You might have heard of twin paradox. Okay, because of this effect, if there are there is a pair of twins. Okay, one of them stays on Earth, other one goes in a high-speed travel, and when they return, you will see that they will have two different ages. All right, that's known as the aging of twins. And the paradox comes because some other confusion. All right, actually, it's not a paradox; it's just aging of twins. Right, there is no paradox; it's just aging of twins. Okay, so the twins who are moving relative to each other age at different rates. Right? Now, it's the same thing that's here, but when you talk about twins or human beings, you see that it's a bit more exciting. All right, it's exactly the same thing. So here is a question. The lifetime of a muon, all right, it's also called a mu meson. Earlier people thought it was a meson, but the lifetime of a muon in its rest frame, right, in its rest frame, let's write it as delta 0, delta t0. Okay, lifetime of muon in its rest frame is 2 into 10 raised to minus 6 second. Okay, right. But are you familiar with the twin paradox? We'll discuss it if you want. We'll discuss the resolution of this paradox in one of the future classes, okay, when we get the time. Or when we look at the geometry, it's much easier. Right? So we have got delta t0 is equal to the same thing you see for muon. Right? Delta t0 is equal to 2 into 10 raised to minus 6 second. Lifetime of muon in its rest frame, right, is 2 into 10 raised to minus 6 second. What distance can a meson travel before decaying if its speed, the speed of this meson is v is equal to 2.994 into 10 raised to 8 meter per second, right? That's the velocity. This is the average lifetime, right? So what's the average distance that this muon would travel before it decays? Okay. We are talking about averages. So how do you find this? Okay. How do we find this? All right. So you have to think about it like this. This is in the muon frame, all right? If you are sitting with the muon, it's not moving in the rest frame of muon. If you're sitting along with the muon, you will see that it takes a time 2 into 10 raised to minus 6 seconds to decay. All right. But if you are looking at a muon which is moving at this speed, you are looking now at a muon which is moving at this speed, right? And what happens to lifetime? You know that lifetime gets changed according to this formula. Delta T 0 divided by square root of 1 minus v square by c square. Okay, you see that the lifetime actually decreases. Right? Does it increase or decrease? Increase or decrease? You see that the lifetime increases. Right? The lifetime actually increases. Okay, so you see that this is equal to just, I hope this is clear, right? This is the lifetime in the rest frame of the muon. If the muon is at rest, if you look at the muon from a frame in which it is at rest, it will take an average of 2 multiplied by 10 raised to minus 6 seconds to decay, right? But now we are looking at a muon which is moving at a speed 2.994 into 10 raised to 8 meter per second. So we know that this lifetime changes according to this formula, right? So it's 2 into 10 raised to minus 6 divided by square root of 1 minus 2.994 by 3 square. All right. Now I think we'll need a calculator to do that. Right. I think we'll need a calculator to do that. So sometimes you can do it without a calculator. I don't know if you can solve it without a calculator. Try, but I think the answer in the end, you have to check this. All right. You have to check this. 31.7 into 10 raised to 10 raised to minus 6 seconds. All right. So this is the lifetime of the muon when it is moving. Right. This is the lifetime of the muon when it is moving. You see that it is greater than the lifetime of the muon. Yeah, it's greater than the lifetime of the muon in its rest frame. All right. So what's the distance traveled by this thing? So you know that the distance traveled, the average distance is, you know that it's velocity multiplied by its lifetime. Okay, it's the velocity and this is the lifetime. So what's the how far can it travel? How far can it travel if it decays in a time delta t? So what's it? We have got a time interval delta t. Just multiply it with the velocity, and you see that the distance, we can write distance traveled by muon d is equal to, okay, d is equal to v delta t. So v is 2.994 into 10 raised to 8, and delta t is 31.7. Yeah. All right. So I think, okay, again, you have to check this numerical part. Check. This is 9,500 meter, 9,500 meter. All right. So we see that the muon actually travels a distance 9,500 meter before it decays. Okay. All right. Now, again, it's interesting to look at it in a different way. What about the muon itself? All right. So in the rest frame of the muon, its lifetime is 2 into 10 raised to minus 6 seconds. All right. And from the rest frame of the muon, if you are sitting along with the muon, if you are sitting on the muon, you would see that this 9,500 meter distance is moving with respect to you. All right. So the muon actually would see a shorter length. The muon actually would see a shorter length. All right. So that's how the muon would explain the thing. So the idea is this. We see that, all right, we see that muons actually travel much greater distances, okay, much greater distances than they normally can, than we expect them to, right? That's because of this relativistic time dilation effect, all right? We would explain it using time dilation effect from the laboratory frame, but if you are sitting along with the muon, all right, you know that the time is 2 into 10 raised to minus 6 seconds. It does not change. Okay. So you'll see that it cannot travel 9,500 meters. But with respect to this muon, it actually does not travel this 9,500 meters. It travels a smaller amount of distance, okay, because of length contraction. So this can be explained in both directions. Okay. All right. Now there was a slightly unfortunate thing I want to tell you. All right, an unfortunate notation that's used. I hope they don't use it in your net exams. I've looked at the earlier examination papers, and this idea of relativistic mass is rarely used. Okay, the idea of relativistic mass. Okay, there is this unfortunate idea of relativistic mass. It's a bad convention, it's a bad notation. It's not used in modern textbooks, all right? But in some textbook, this notation is still used. Okay. So then it's not really nice, but if they use it, you should know what it is, all right? If they use it, you should know what it is. So I'll just say these two concepts. We have got these two ways of looking at it, all right? So there is this relativistic mass camp, okay, and there's the camp where the relativistic mass is not allowed. Mass is not allowed. Okay, it's a bad idea. Okay, so in this camp, right, people say that the rest mass of the particle of an object has to be taken as m0, right? The rest mass of the object has to be taken as m0, all right? And then the momentum, okay, you see that for momentum conservation, the momentum 3 vector has to be gamma m0 v. Right? So they are actually doing a bit of cheating. In Newtonian, we have got mv. Okay, so this m, they call it as m0. Newtonian, whatever we have as m, they call it as m0. And we know that p for momentum conservation requirements say that the momentum cannot be m0v, but it has to be gamma m0v. Right? So people say, all right, this gamma m0, okay, gamma m0, we can call it as a new mass m. Okay, and then it has the same form. The momentum has exactly the same form as before. Okay, so they say that this m is gamma m0, so mass is relative. Mass changes with respect to motion. Right? Now this is a very bad convention. It's actually sufficient. This people say, this camp actually says, in modern notation we say that there is only one mass. There is only one mass. Okay, that's the rest mass, and we always call it as m. There is only one mass. We always call it as m. That's the rest mass. Okay, this is the rest mass. Okay, what about momentum? Newtonian, this is given as mv vector. In relativistic, of course, we have to change the old notations of Newton. We have to use gamma mv vector. No problem. We don't put gamma mass, a new mass. Okay, the mass is always the rest mass. There is no relativistic mass. Okay. Now, this is the notation used in all modern textbooks. If you look at electrodynamics by Griffiths or even Arthur Baser or any modern textbook on relativity or electrodynamics or mechanics, even if you take Goldstein mechanics textbook, classical mechanics by Goldstein, there is no this confusing relativistic mass thing. Right? So mass is not relativistic, all right? It's a, we see that this quantity is a Lorentz invariant quantity. It does not change. It does not change when you go from one frame to another. Okay. Here, this m0 is also relativistically invariant. Okay. So here there is a problem because we have two kinds of mass. We have got relativistic mass, which we call as m, which changes with speed. Okay, which changes with speed, and we have got a rest mass, which does not change with speed. Does not change. Okay, here we have only one mass, and that's Lorentz invariant. It does not change with velocity. Okay, now I prefer this notation, and in most question papers, the rest mass is always taken as m, and they don't use the concept m0. Right, but if m0 is used, you should know what to make of it. Right? There's another reason why this is not a good notation. Okay, because we know that in this case, okay, where relativistic mass is a bad concept, E is given as gamma mc square. Gamma mc square. Now, if you expand this gamma is the Lorentz factor 1 by square root of 1 minus v square by c square. If you expand this and take the first order term, and if you take v much less than c, you will get back the old kinetic energy plus a relativistic correction. All right, E is equal to gamma mc square. All right, and here what they do is that here E is equal to gamma m0 c square, and what do they do? They say that this gamma m0 is m, so they write it as E is equal to mc square, where this m is the relativistic mass. All right. Now, if you look at this, you see that this energy and relativistic mass, this is the relativistic mass here, all right? Mr. This energy and relativistic mass change only by a universal constant. Okay. The concept of relativistic mass, from this equation, you see that the concept of relativistic mass, what we call as m, okay, this changes. This is different from the energy only by universal constant, right? So this means that energy and relativistic mass have the same physical content. They have exactly the same physical content. Okay, so there's no new physics in the relativistic mass. What you mean by relativistic mass is actually the energy content. Okay, so now here what we have got two different concepts with exactly the same physical content. And it's extravagant. We don't need it. We have if you use energy, you don't need relativistic mass because it's exactly the same physical content. And in some cases, we'll in modern notation, we'll sometimes take C equal to 1, right? Then you see that mr is exactly equal to the energy. So there's no need to keep both energy and relativistic mass. It's sufficient to use energy and rest mass. That's enough, all right? Because energy and relativistic mass are exactly the same thing. Okay, so that's the reason why relativistic mass is a very bad idea. People don't use it nowadays, but if they use it, you should know how to deal with it. All right. So in this notation, we'll always write P is equal to gamma mv and E equal to gamma mc square. So we won't use E equal to mc square. No, this is not true. Okay, we can say E rest. The rest energy is equal to mc square. Okay, E at rest, when the particle is at rest, its gamma factor is 1. So E rest is equal to mc square, but E equal to mc square we don't use. Here they use E equal to mc square. Okay, so it's always good to use E is equal to gamma mc square. Right? And there is no problem because energy is not Lorentz invariant. It changes when you go from one frame to another. Right? Energy can change when you go from one frame to another, but mass does not change. This is all nice. Okay. So here you see that to say that relativistic mass is relative, the mass changes. When you say that relativistic mass is relative, what you're actually meaning here is that energy is relative. All right. In this notation, when you say that mass is relative, what you actually mean is that energy is relative. Okay, and energy is obviously relative. There's no two opinion about it. All right. So this concept is completely unnecessary. We don't use it. Okay, I won't be using it. Right? We'll always use E equal to gamma mc square. Right? Is there any doubt regarding to this? Okay, so there's no confusion because energy has to be changing. If the particle is at rest, we say that the kinetic energy in Newtonian notation, kinetic energy is 0. But if you are moving at a velocity with respect to it, you will see that this particle is moving in opposite direction with velocity v, and it will have energy half mv square. Okay, so it's obvious that energy has to change when you go from one frame to another. Right, and mass is invariant. So when you say that here, again, I repeat, when they say that mass is relative, actually what they mean is that energy is relative. Okay, so we don't need two concepts of mass. We just need the concept of rest mass. Okay. All right. Is that okay? Is there any confusion? Any questions?
No, sir.
Okay, good.